won't be a lot of mathematical formulas here. So this is an application. So hope I won't get you bored. And yeah, I'm detecting anomalies in digital markets on the basis of cryptocurrency market as well as information market. Information market is something in the literature which is also described as social network. So basically that are two areas of my interest. And they are subtypes of digital market, which is basically meaning that instead of relying on physical presence of both entities and subjects of the transaction, it is switched to online channels. So of course, this has lots of efficiency gains, like lowering different types of cost, like search cost or cost of verification of the subject of the transaction, for example, rating platforms. But at the same time also generates some risks. And about risks, I will tell you soon. But what is interesting here is that these markets have very interesting property for us, which is they're able to be described as graphs. While users are represented as vertices and some interactions between these users, these market actors, some interactions as an edge. So interaction may be, for example, a transaction or any kind of connection in social network, like subscription relationship. For example, relationship of following in the Twitter data. So that is why it's interesting for us. And I would like to focus on digital markets, which are peer-to-peer networks, which basically means that there is a crucial role of trust in this kind of market. So no external regulator. That is why detecting anomalies may be important. So I mentioned several efficiency gains about switching the channel to the online one, but of course there are some kind of risks in these markets as well. We were talking during that conference about spreading fake news, and this can be done using artificial accounts or fake accounts to spread the information in a more extensive way. Why is it so dangerous? Because it may polarize political discussion, seed discord, or even influence political decisions. For example, as an example myself, Cambridge Analytica case, or even Brexit, because there is one interesting thing that actually after Brexit, 15,000 Twitter accounts just disappeared out of nowhere, and main topic of these accounts was actually Brexit. There is even a term in the literature, computational propaganda, which is basically describing a way of influencing society by means of online channels. So that is particularly interesting in the context of cyber wars. That is why I believe detecting anomalies is useful here. On the product market, on the other hand, it may mean influencing not only political but consumer patterns, like for example, issuing fake reviews or even failure to fulfill an obligation, or even some fraud on financial market, like insider trading, or in the case of cryptocurrency, hiding some black market activity. Due to architecture of cryptocurrency, it's easier to hide there. So one common feature of these two subtypes of digital markets is that they're not yet regulated enough. Actually, there is upward trend in regulating this, because last year, actually, I believe there was first conviction of insider trading in cryptocurrency network. So yeah, this trend about detecting anomalies and regulating these markets is more and more persistent. So I already told that this can be represented as graph. So how can we use graph in the analysis? Now I will show you what kind of data do I use. I have 3 data sets, and these are real data. First is Twitter network. So basically this is not whole Twitter network, obviously that would be difficult to obtain. But instead of focusing on some particular topic, because usually in the literature, Twitter network is sampled in that way, just particular topic or particular geographic location, authors of the paper about this data set, so Feng, they perform something in more diversified way. So just select some users from diversified geographical location or diversified areas of interest, and then follow their relationship of following, because in Twitter it's following, up to layer 3. So this is described as more natural representation of Twitter sphere. This graph has 150K nodes around, so that is quite large. And it is supplied not only with graph data, but also user profile characteristics. And interesting thing about that one, why I also took Twitter, is because we have text data. So we can actually check whether features extracted from text are performing better or worse than graph one. And the difficulty in anomaly detection on real data is that we don't really have usually labels here. We don't usually have ground truth. And authors of this paper actually annotated bots manually by using external annotators. So these annotators, only requirement for them was just to be Twitter user and follow some guidelines from researchers. One of these guidelines was to base on user profile characteristics. And for example, if the Twitter profile was verified, then the participant of that market needed to be described as non-bot, so not an anomaly. That is why I believe usage of this user profile characteristics can be a little bit biased. It's like designing the problem and then designing a specific algorithm to solve that particular problem. However, two Bitcoin networks, because I have two of them, they come from two different Bitcoin markets. They mitigate these two flaws of Tweebot dataset. So first of all, they are representing the whole network, which is actually good because we know results can be more stable that way. And second fact is, and that is, I believe, quite unique in this kind of datasets, that we have some kind of objective ground truth here. How is that constructed? So authors of the original paper, where these datasets are coming from, so Kumar et al., they extracted founders of the platform as well as users positively rated by them. So we know that they are actually normal users, so benign users, not anomalous. And users rated negatively by these normal users can be described as anomaly. Okay, so that is why these datasets are very interesting. By the way, I didn't tell you what actually is represented here by node and of course by node user, but what is an edge? It is not actually a transaction. It is a proxy of transaction, because these markets have such kind of property that after transaction user can be rated. Okay, so edge is actually fact of being rated, but as we can see, as it can happen after the transaction, it is a very good proxy of transaction, and only users with positive rating can do that. That is why it is not that very much biased. Okay, so 3 data sets, and yeah, just to go back for a moment. So in Twitter we have text data, we have user profile data, and in Bitcoin just graph data. What are challenges around this one? Why did I decide to take a look in actually graph extracted features? Because to extract features from text, it is not that easy. First of all, it requires some engineering, and the cost of training model is quite high. Of course, there are some pre-trained models, but they're not time invariant. So let's imagine another phenomenon appears, like for example, COVID or a different kind of topic, and we cannot just train this model straight away. There are, of course, some privacy concerns around this one. To conduct analysis on the basis of maybe a little bit private data. But I believe the most important one is that with advance of new text generation techniques like ChatGPT, even for human eye, it is difficult to distinguish automatically generated text from text written by human. So it would be kind of easier for a bot to pretend that it's actual human. But for graph data, it is not that easy, on the other hand, to replicate the whole graph structure and pretend that you are a normal user. For that, you would need to have lots of nodes, like lots of users, and that would require probably something called troll farm in the literature, which is possible but quite costly, both in time and financial. So yeah, on the other hand, we have graph data, graph extracted data, and what they can actually be. First of all, we can extract node statistics, okay? So like degree for each node and so on and so forth, different kind of importance measures. But one may say, okay, but it is too simple. Why would I like to use that if there are different kind of embeddings? Yeah, but for embeddings, which one should I choose? There are plenty of them. Either classical, either structural, which one? And also, what dimension should I use? Should I compress or not? Another factor why can be they problematic is that on larger graphs, so for example on Twibot, and just to remind it is 150k nodes, some embeddings, so struct2vec as well as I believe graph convolutional network, did not actually complete at all. I got a memory error, but it's probably fault of implementation. Maybe I should use Julia because I use Python. Because for sure I did not lack memory. I set up AWS machine with lots of RAM and made some swaps. So I'm sure that was not a memory, especially that other embeddings run. So how can I choose optimal algorithm for anomaly detection or any other task? I should probably prepare all of them in all dimensions and then determine which is performing the best. But as we can see, even one is a lot of time and work. On the other hand, no statistics for Twibot completed in several minutes. So if we can have this kind of gain in efficiency, that we can obtain informative features in several minutes and use them efficiently, I believe it would be great, because graph sizes are ever growing and networks are changing constantly. So for anomaly detection or any other kind of task, that would be actually very helpful to have this kind of quick features, okay? These are sets of features which I extracted from text data. On the left-hand side, profile data, just, out of curiosity, because I don't really use them. I believe they're a little bit biased because actually what is bot and what is not bot was annotated on this basis. And on the right-hand side, what text data do I have? So any kind of features regarding numbers of tweets, average length of the tweet, standard deviation of tweet length, variety of language features, like for example, number of languages used or percentage of English tweets. According to the literature, bots are often using negative content. That is why sentiment as well. And that is why something like number of links included and number of mentions included. So mentions of other users, because in the literature it is believed that bots are not always creating their own content, but just reposting. Okay, graph extracted data. This is list of features. Yeah, no statistics are used, so different kind of importance measures. And except for that, I computed also statistics like average, standard deviation, minimum, maximum for their neighbors, up to order 4, and embeddings. So both structural and classical. The two last one were not created for Twibot because it was not possible. Yeah. And this slide is a high-level overview because, as you can see, I have lots of features, lots of embeddings and so on. So what is my task here? My task here is to determine what kind of set of these features is performing best regarding anomaly detection. And how do I do that? Each set of features, like no statistics and any kind of embedding, was prepared in different variants. And then every set of these features was used to create model for anomaly detection. So for each dataset, it was like 150 models. And then these models were performed according to their F1 score. I will present also other metrics, but why F1 score is important is that because it is good for unbalanced data, and anomalies are usually considered to be unbalanced because of you know, we don't have much anomalies. So yeah, each embedding was prepared in different dimensions. Each dimension above 16 was also compressed using both PCA and UMAP. So it's like we have embedding, one data set, then compressed embedding with PCA, then with UMAP. Similar with no statistics. Also, all embeddings compressed using both PCA and UMAP, so separate data sets, as well as no statistics compressed with best performing embedding, and statistics of node neighbors up to order 4. So just high-level overview, and each of these sets was plugged into model. And just to save me, you know, hypertuning of these models, I used AutoML package in Python, which helped me to tune these parameters. These are some technical details around it, but maybe not very useful for the purpose of this talk. If you're interested, we can discuss it later. But the most important thing is that parameters were tuned automatically, and then for each set of features, I have the best model in its class. So I can compare them using F1 metrics on the test set. So this is a metric of model performance, and it is like accuracy, but it is better for unbalanced data. Like if you have imbalance or a sample, for example, in that case, not equal number of anomalies and non-anomalies. So you can think about it like performance measure. Yeah, thank you for the question. And let's see. Okay, this is just some motivation behind it. So probably we don't have time for that. But for example, on Twibot dataset, let's see. Here, only 10 models. Actually, there were around 150 of them, but of course, I will present only the 10 first. So what is interesting here is that actually graph features are on the, so graph features is another name for node statistics, are on the 5 first places. With F1 metrics 77%. Interesting thing is that actually best performing embedding is node to vec. And why is that interesting? Because it's classical one. So it does not take into account the whole graph structure. And maybe we can be surprised about it at the beginning. But then remember that that network was actually sampled. This was not the whole graph. So maybe that could be the reason. And we can see there is one specific embedding performing the best here. It is not easy to determine really if compression helps or not, because some of them, I don't want to break it, okay, because compression is in this column, so some of them actually were compressed version in the best 10 one, some not. So it's hard really to determine whether it actually really helps in every case. Of course, not in every case, but no general rule should we compress or not. And what else can we say here? We can say that actually there is some benchmark from the literature, which is, let's see, F185. And okay, you may think, so actually our data is performing far worse. But in the other work we were doing on Twibot data, we used user profile characteristics, and it was very easy to replicate this result. That is why I think these user profile characteristics are biased and did not use them here. But another interesting thing is that we don't have text features on that list, okay? So that is actually pretty interesting insight. So graph extracted features perform better here. But what about other data sets? Bitcoin Alpha, another time, graph features on the first 2 places. This time, the best performing embedding was struct2vec, so structural one. So we already can see the choice of embedding differs between datasets and tasks. So probably that is nothing we can think of in advance, because it may be case specific or dataset specific, and only way to determine which would be the best is to create all of them and then check. Yeah, that is one thing. And the second thing is that this time we have the whole network. And it was very easy here to replicate. This is a AUC matrix, which is here. And this time it was easy, quite easy to actually outperform this matrix. Authors of these papers actually performed comparison of like 7 state-of-the-art algorithms. So I believe it is very interesting that with no statistics, it was easy to outperform it. Yeah, so Struct2Vec mainly here. And how about other Bitcoin network? This time, I won't lie, graph features are on the 5th place, so not the best performing. But interestingly, the best performing embedding is actually based on node features, node statistics. That is only one, I think, which is actually processing node features and their distribution under the hood. What we can also see here, that this time, best performing embedding is different. It is Rolex. So again, not possible to determine the best embedding in advance. And again, we outperformed the metrics from the literature, comparison of like 7 state-of-the-art algorithms. That is a good information. So different rankings, okay? We have different rankings here. Oh, actually, this is just models grouped by their embedding type, and again, F1 score, just to see. But what is interesting here is that graph features, even though sometimes they perform a little bit worse, as in the last case, they're still pretty stable, and there is not much loss in accuracy. Why I say that? Because here they were on 5th place. Sorry, not in accuracy, but F1. That's what I look at. So just a little bit. While, for example, if we use the worse embedding, okay. Did I break it? Yeah. If we use the worst embedding, we will lose less than 10 percentage points. So I believe graph features, no statistics, are performing really stably in that matter. And the gain here is not only better performance or more stable performance, but we can actually avoid this kind of embedding choice, preparing all of them in advance, preparing all dimensions, and then picking them by modeling like me. I spent really several, not even hours, but days preparing all these embeddings on these data sets. No statistics we can just have in several minutes, and even in the large graph. And then in an easy way, we can just connect them with no statistics of their neighbors, which is actually maybe not embedding in its pure sense, but it is kind of vector representation of the graph. So yeah, I believe that is all I wanted to say. This is just figures about dimensions, and the key outcome. I think I already covered them before that slide. This was like extra slides. So yeah, no statistics, pretty efficient and pretty stable in anomaly detection task. That is main conclusion.
Thank you very much.
Thank you.